Okay, so good evening. So shall we start? Okay, so last time we talked about the introduction. So let's wrap it up today. So last time we talked about the 3 machine learning paradigms. Okay, so the first one is supervised learning. So in supervised learning, what do you need to provide? So in supervised learning, we have input X, okay, and so you have to give me a training set, right? Okay, in the training set, each sample consists of the input X and also the corresponding label or regression value Y. Okay, so this is supervised learning. In case, maybe we just go back. So recall that this is the idea. So you need to have a so-called teacher. Okay, so you have the input X and then also the corresponding label Y. Okay, so this is supervised learning, and so this is commonly used in lots of applications, and then it is very informative because you have the teacher. But however, sometimes there is a problem. The problem is that so you need to have a teacher, you need to have labels. So in some applications, you may not have the teachers, right? So maybe collecting the label is very expensive or may not be even feasible. So in that case, you can do unsupervised learning. Okay, so in this case, you're only given the input, okay, but then there's no label. And so what you can do is, say for example, clustering, by observing a lot of these samples, then you can gradually see that, okay, so these are very similar, and then this one is very different from all these. Okay, and so you can do some grouping or clustering. Okay, and so in order to do clustering, you need to have a similarity measure between the samples. So besides clustering, you can also use this for dimension reduction. Okay, so in this case, you reduce the dimensionality of each point from 2 to 1. You can also use this for outlier detection or anomaly detection. So meaning that you think some points, say for example, this one is very different from all the other points, and so you think that this may be an outlier. Okay, so this is unsupervised learning. And then the third learning paradigm So, and of course, you can also use unsupervised learning, okay, for data generation. That is, you're given the X, okay, lots of X, and then you try to learn the underlying data distribution, and then after that, you can draw samples from the learned data distribution. So this data can be images, okay, and then you do image generation. This can be, say, time series, can be natural language, can be whatever, okay, and so this is unsupervised data generation. And so the last major learning paradigm is reinforcement learning, and in this case we still have input-output, but then the output is not as informative as before. So it is just what we call an evaluative output. So what that means is, so recall this in supervised learning, so you have to provide the input, and then in reinforcement learning you also have the input, but then in supervised learning, so you have this teacher, okay, teacher will tell you what this is, okay, say this is a spider. But however, in reinforcement learning, as you can see, so this person, so we now call a critic, so does not give you explicit label information, okay? He just criticizes your answer. So say, for example, you look at this, and then you think this is lizard, and then this critic only tells you that you're wrong, okay? But however, it does not tell you that this is a spider or whatever. So you only know that you're wrong. And then you have to somehow, based on this, what we call the reinforcement, okay? And try to adapt your model. Okay, so the reinforcement, well, if your answer is correct, then you will get a positive reinforcement. Say, for example, you can get some positive reward, okay, give you a point, something like that. And then if you're wrong, you will get a negative reinforcement. So basically the idea is you have a lot of these exchanges, okay, trial and errors, and then you try to maximize the total amount of reinforcement that you can get. So last time we said that this is similar to having a grade exam, but you only get the overall score. Okay, so I don't tell you that you got 80 marks, and then the idea is, well, you have to learn from this. So basically what that means is that, okay, this time you get 80 marks, you try to improve in some way, okay, hopefully you can get better marks next time, and then you take the second quiz, okay, and then if you get only 60 marks, then you know that what you did, okay, is not good, okay? But if you get, say, 90 marks, then you think you are moving in the right direction, and so on. So as you can see, so you can still use this kind of reinforcement information to improve, but obviously it is not as informative, and so it can be very slow. However, so reinforcement learning has been very popular in recent years, okay, particularly with the rise of the LLM. And so this is an earlier example a few years back. So what it did is that this is a Rubik's Cube, okay, but this is a physical Rubik's Cube, okay. And so what they did is that they used a robot's arm to solve this Rubik's Cube, okay. And moreover, so what they did is that they try to make this problem more difficult. So say, for example, they add say slippery surfaces, okay, they add in different sizes, and so on and so on. So if you're interested in this experiment, okay, so this is again done by OpenAI, so you can look at the videos and the links. So later on we'll talk about the reinforcement, if we have time, okay, we will talk about reinforcement learning. But basically reinforcement learning can be formulated as the figure on the left. So this is you, okay, the learning agent. So you are trying to interact with the environment, and just like in the previous example, you try to say give a correct classification of the input image, okay, and so you can say you are basically correct performing some action, okay, or just like the Rubik's Cube, you try to use, okay, manipulate your fingers, okay, and so each possible manipulation is an action. So you try different actions, and then you perform these actions, and then of course, so in the case of the Rubik's Cube, then the environment also includes the cube. So you move the cube, okay, and then you move the cube, and then of course you will get some feedback. So the feedback is that you will get some new state information. Okay, so how the curve now looks like, and you also get a reward. So say, for example, the curve falls down, then of course you get a penalty. Okay, or if you solve the curve, then you get positive feedback. So again, the idea is that you try to maximize the total reward, okay, or reinforcement, well, by performing a sequence of actions. Okay. So one application is that you can use this idea to, say, for example, do stock market investment. So in this case, the action can be, say, buy and sell. Okay. So you buy and sell, and then of course after this action, then well, you get some reward in the state. So say, for example, you buy some stocks, and then of course you get some more stocks, but then the reward, okay, can be positive, can be negative. Okay, so say, for example, you sell some stock and then you lose some money. Okay, so again, the idea is if you play this stock market price for a long time, so hopefully, well, you try to maximize the total amount of reward. That is, you try to make much money as possible. Okay, so that's why, again, you can learn from this RL setting. So, yeah, and a more simpler example, okay, is a standard example in reinforcement learning is pole balancing. So again, just like before, you can define actions, rewards, and states. So in this case, pole balancing, so what that means is that you imagine that you are a cart, okay, and you try to balance this pole. Okay, so in this example, so we are living in this one-dimensional world, so you can only either move in this direction, to the right or to the left. Okay, and then you try to balance the pole, so as long as possible. So, of course, well, you can use supervised learning. Okay, so if you do supervised learning, then how to formulate this as a supervised learning problem? So recall that for supervised learning, so you have to provide a data set, and this data set has X input and Y output. So if you want to formulate this as a supervised learning problem, then what do you need to provide in the training set? So what is the X? Yeah. Yeah, so what is X? So you have input, output, right? Training set, supervised learning. What is X?
How much the yield should return?
How much?
The yield should return.
So X is the input. Okay, you have this input, and then you map to this output. Okay, maybe talk about the output first. What is the output? If you want to train a supervised learning model, so how should you define the output? The angle. So you want to predict the angle. Fall or not. So basically, so you want to balance the pole, right? Okay, so you want to solve this problem. So that's the problem. So say, for example, in other words, what do you need to do? So this is kind of like driving a car, right? But this is a much simpler autonomous driving example. So in driving a car, so what is the input and output?
Input is some movement, I guess. What I'm thinking is X is, I guess, the position of the car, and theta is the angle of which the ball is pretty much leaning towards the floor, and it's supposed to be 90 degrees, because we're balancing it, right? And we're moving, as I'm thinking, X in such a way that it keeps the 90 degrees.
Yeah, of course, you don't need to be 90 degrees, okay? You just don't want this to fall down. So in autonomous driving, okay, so we talked about this last time. So basically, so in autonomous driving, okay, so you look at the image, okay, so this is the image that you capture from your camera, so this is the current flow condition, and then you have to, say, determine the steering direction. Okay, of course, in practice, you may also need to determine the driving speed, whether you want to brake or not. Okay, but anyway, the input is the image. Okay, of course, this is a much simplified scenario. In practice, besides this camera, you also have lots of more sensors. Okay, suppose that you only have this camera, and so this is the input, and then the output is which direction you have to choose. Okay, so this is control. So in this pole balancing, so this is kind of like a simplified driving experiment. So what are the actions? So in driving, so in the previous example, I can steer in this direction, turn left or turn right. Okay, in this one-dimensional case, you are the cart. Okay, it is only one-dimensional, so the only allowable actions are either you move to the left or move to the right. Okay, only two outputs. Okay, either go left, go right. So what is the input? So basically, in control, okay, you want to determine whether I want to go left or go right. Okay, but then what is the input? So again, just like driving, okay, for driving you have the current road image, and then in this case, again, so you have to basically look at the current configuration. Okay, so what is the current configuration? So that means that you need to, okay, so here we assume that the cart can only move between these two bounds. Okay, so of course you have to see how far you are away from the boundary. Okay, so basically tell your position. And then you also want to know whether the pole is falling down. In other words, I want to know this particular angle. Agree? So, in fact, this is the input, okay, the combination of the X and the data. This defines the configuration you are currently in. And then the output is, well, if I'm in this situation, so should I move to the right or to the left? Okay, so that is the Y. So of course, as a human, we all know that if you are in this situation, you should move to the left to the right. To the right, right? So that means that if I want to solve this problem by supervised learning, then what should I do? So as I said, you have to provide me with training samples. Yeah, exactly. So you have to give me a lot of training samples. So each sample will be like, this one, go right. And then this one, so this one, go right. Okay, and then this one, go left. So you have to give me basically a lot of these examples and so on and so on. Okay, and then you can feed this into a feed forward into a supervised learning model. Okay, so basically in this case just a classifier, two classes. Okay, and then you can learn what you should do. But however, well, as I said, you can do this in a supervised learning manner. But however, obviously there is a problem. So I suppose all of you know how to do this when you were a kid, okay, or when you were a kid, you learn to play with this kind of game, okay. So did you solve this game by supervised learning? So did your parents tell you that, okay, if you are here, you should go right, if you are there, you should go left, and so on? No, because you don't want to do it by supervised learning because So why didn't your parents do this? Because it is too tedious, right? So typically in this kind of situations, okay, you don't want to solve this by supervised learning, okay? So in other words, okay, you don't have the why, okay? But then you can use reinforcement learning, okay? So how to do this by reinforcement learning? So as I said, so you have to specify the states, okay, so basically the states are the configurations, okay, that is, as I said, the X at the data, so you know that currently I'm in this position, okay, in this configuration, and recall that in reinforcement learning we have to define, now we call the actions, okay, but basically the actions are, as I said, going to the left or to the right. Okay, but then one more thing is missing, so in reinforcement learning, we also need to define the reward. Okay, so the question then is how to define the reward. So recall that we want to define the reward in a such way so that if you can maximize the total reward. Okay, so recall that you have to play this game a lot of times. Okay, so maybe in the first time, but at the very beginning you don't know what to do. Okay, and then when you are here, you still go left. Then of course what will happen? So the pole will fall down. Okay, and so you fail. Okay, and so next time, okay, well, game over, okay, and then you start the game again, and then you play again, okay, maybe here you still don't know, you fall down again, you game over, okay, and do this again, and so on, so on. So you try this a lot of times. So the idea is, well, when you game over, okay, of course you don't want to get 0, okay, so you want to stay here as long as possible. You want to define a reward such that, well, by maximizing the reward, you can stay in this position as long as possible. So now the question is, how can you define the reward in such a way that at the end you can achieve this goal? So one example is that you always get 0, okay, until when you fall down you get -1. So basically what that means is if you are still in this kind of state, okay, you get 0 reward. So 0 reward is not good, but at least it is not bad. Okay, and then when you fall down, the pole falls down, okay, you get -1. That is you fail. Okay, and so you do this a number of times, okay, and so you try to maximize your reward, that is try to minimize minus reward, right? You try to minimize the number of -1 you get. And so essentially, if you can do this, then you're basically trying to get 0 all the time. In other words, you are basically always maintaining the pole in this direction, in this situation. Is it clear? Okay, so this is basically reinforcement learning. So of course, you can see that, well, since, as you can imagine, so basically most of the time you get 0 reward. Okay, so if you're here, you really don't know you are doing good. Okay, but when you have this, then you know that you are doing bad. Okay, and then you know that something has gone wrong, and so you try to correct for this. Okay, so obviously this is not as informative as supervised learning, because supervised learning, well, your parents or your teacher will tell you that, okay, if you're here, you have to move to this direction. Okay, so this is very clear what you should do. However, for reinforcement learning, you have to try. Okay, and then until you get some non-zero reward, you know that you have to do some modifications. Okay, so there are many other scenarios. So say, for example, this is a mountain car example. Okay, so I suppose you have played this kind of game before. So how many of you know how to drive? Have a driving license? Okay, good. So suppose that you are driving this car. Okay, so unfortunately this is a very old car, and you want to go to the peak. Okay, and you are driving a very old car. So your car is too old, and so you cannot go to the peak. But still you want to go to the peak. So what should you do? So you have to try some dangerous way of driving. Okay, so what should you do? Yeah, so in this case, maybe you have to move to the left, and then, so you move to the left, right, and then you let it free fall, okay, and then you go to the left, and then go to the right, and then swing, okay, and then you will be able to swing to the top, okay. Of course, well, it is hard to do this by supervised learning, right, because nobody will give you, well, this kind of supervised training set, okay? So what you have to do is to do, again, reinforcement learning. You just trial and error, okay? So now, obviously the goal is to go to the goal, okay, go to the peak. Say, for example, we also want to minimize the time to go to the peak. So just like before, so the state, what are the states? So you need to know what kind of situation you are in. So for this problem, maybe you can say, well, you can specify the car's position and velocity. Okay? And then the actions, what are the actions? For this simple car, all you can do is, forward, backward, okay, or nothing, okay. And then now, the tricky part is you have to define the reward. So again, you have to define the reward so that if I can maximize the total reward, I will be able to go to the peak. So how to do this? Yeah, so again, very similar to what we have before. So basically, we just do it a little bit different. Okay, so here, at every time point, you get -1 until you go to the peak. Okay, so what will happen? So suppose that you're here. So you're here, you are not at the peak, so you get -1. You swing, okay, and then here you are still getting -1. Okay, in all these parts, you are still getting -1. Okay, so at each time point, you are collecting a lot of it, -1. Okay, and then when you are here, then you get 0. So again, just like before, you don't want to get so many -1, right? So just like in the midterm final exam, you don't want to get a lot of mark deductions. Okay, so by reducing the number of -1s, essentially, you are finding the best way, the fastest way to go to the peak. Is it clear? So that's how by carefully designing the rewards, okay, and then you let the agents learn to maximize the total reward, and then you will be able to achieve the goal. So reinforcement learning is commonly used, say for example, in say robotics. So in robotics, oftentimes we have to explore the region, okay. So say for example, you send a robot to the moon or some unknown places, then it needs to, okay, navigate itself. So obviously, when you're doing a robot, okay, you want to avoid something. You want to avoid what? So you want the, so you will get penalty if what? If you hit if I hit you, right? Okay, or I hit the wall, or etc. So basically, again, so the input is basically the current configuration. So you can use cameras, you can use various sensors, and then the output is again the various actions, okay, left, right, and so on. And then the goal is that you want to avoid negative reward. So say for example, you want to avoid obstacles, and if you hit into an obstacle, you get negative reward. Okay, if you can follow a certain path, then you get positive reward. And so the goal is that you try to maximize the total positive reinforcement. Okay? So of course, even after defining the reward, you have to somehow figure out a reinforcement learning algorithm, okay, of achieving this. So you can also combine reinforcement learning, okay, with deep networks, and then recall that here we have this agent, okay, and if this agent is a deep network, then you have a deep reinforcement learning, okay, which is very commonly used these days. Okay, and so for example, this has been used for game playing, okay, Atari, Minecraft, and so on, and AlphaGo, and Dota 2, and so on, etc. Okay, so if we have time, we will go into the details of this. So, any questions? So this finishes the introduction, and so next. So we are going to talk about the supervised learning. Okay, so for supervised learning, so we will start with the most basic models, which is a linear model. Okay, so recall that for supervised learning, that means that so we talk with linear models. So in particular, well, as the title states, we will talk about both classification and regression. Okay, we will first talk about regression and then classification. And recall that in supervised learning, we want to learn an input-output mapping. Okay, so we have some input x, and then we have the output y. Okay, and so this is the model that we want to learn. So we have, as I said, depending on the output, okay, if the output is a class label, okay, I want to classify this input x into a number of different classes, then this is a classification problem. Okay, so the simplest type of classification problem is a binary classification. So binary means that we have only only two classes. Okay, so two classes. So y is the class label. So we can use a +1 -1. Okay, or you can also use 0 1 if you like. So you have only two classes. So of course, well, for 2 classes, so there are already a lot of applications. So say, for example, you want to look at whether a particular credit card transaction is fraudulent or not. Okay, that is fraud and fraud. Okay, you can look at monitor the comment. Okay, on a social network, you can do sentiment analysis. Okay, so the sentiments can be positive or negative. Okay, so of course, more generally, you can have more than 2 classes. Say, for example, so for binary classification, I can also do, say, for example, I look at this image, and then I want to see whether this is what? So I look at this image, I want to see whether this is a positive face or negative face. So in practical applications, you look at a face and then want to see whether this is male or female, right? Okay, so say, for example, I'm running a shop, and then I install a camera at the entrance. I saw this person coming in, and then I capture the face, and then my model tells that this is a guy. Okay, then maybe I can do personalized recommendation. Okay, I recommend him to buy things that guys buy. Okay, say, for example, a game. Okay, whatever. Okay, and then but if this is a lady, I may recommend something else. Okay, so this is a binary classification, male, female. But oftentimes, you can also do more than 2 classes. Say, for example, so again, I look at this face. Okay, I'm still running the shop. Okay, I look at this face. Instead of predicting or classifying that this is a male or female, I can also do, what else can I do? What kind of classification problem can I do? Yeah, okay, maybe occupation. Okay, whether it looks like a student or looks like a manager or looks like a whatever. Okay, but maybe I can also do, say, age estimation. Okay, whether he's an old guy, okay, or middle age, or a young guy, or a boy. Okay, so I can do, in that case, I have 4 classes. Or maybe I can also see, okay, whether this is an Asian, or European, or American, or African, and so on. Okay, and then I can, based on that, I can predict the corresponding items that he or she may want. Okay, so in that case, this is a multi-class classification problem. But of course, the simplest is 2 classes. Okay, and then when you have k classes, then that becomes a multi-class classification problem. Okay, so regression is again similar. So this is supervised learning. Okay. And so recall that if you want to train a model for this, you have to provide me with x and the corresponding y. Okay, and for regression, it is similar. In that case, the output is not a class label; it's a number, okay, or a vector of numbers. So again, there are lots of examples. Again, so if you use this face image, okay. Again, I have this camera at my store. I capture this face image. Then what kind of regression problem may I want to do? Yeah, so again, I can do age estimation. Okay, so previously, I just predict whether he's old or young or middle age and so on. Okay, but I can also do age estimation. I can predict his age. Okay, maybe 21 or 52, okay, and so on. Okay, I can predict a number. Okay, so which one is better? It depends on your application. You can predict the exact age, right? Or you can just predict, well, which category he belongs to. Okay, so if you predict a number, then this is a regression. Okay, or I can also look at his face, okay, and then I predict, well, how tall he is, right? And in this case, this becomes predicting the height, which is again a number. Okay, so this is a regression problem. Okay, or if you have a very smart model, you look at his face and then you can predict how much is his salary. Okay, so he may be earning $1 million per month. Okay, then this is a regression problem. So again, so you can have a lot of real world applications. So say for example, you have the housing in Hong Kong. So housing is very important. Okay, so you look at the specification of a house or an apartment. Okay, and then you predict how much should be the price. Okay, so again, the price is obviously a number, so this is a regression problem. So you can as we have seen, so you can predict a class label, you can predict a number, okay, or more generally, your outputs can be another object. So say, for example, I want to do translation, okay, then the input is a piece of text. Say, for example, in English, I want to convert that, the output is a piece of text in Chinese, okay? So a piece of Chinese text is not just a random, right? So it has some structure. Or some of you may have a biology background, okay? So I may be given some properties. I want to output a molecule, say for example. Okay, the molecule again has a structure, so this is complex objects. But of course, for simplicity in this course, we don't talk about structured data in this case. Any questions? So let's first talk about regression. Okay. So recall that regression means that I have the input and then I want to obtain a number. Okay, that's output. So here's a simple example. So recall that you have to give me some training data. So we have the training set here. So in this simple example, we have one-dimensional input x and we have one output y. So this is the input. So 1, the corresponding output is 1. 2, corresponding output is 3. So this is a number. Okay, so this is a regression problem. Okay, so again, so the idea is, so you are given this training set. You want to go through some algorithms and then produce a model. Okay, so once you're given a model, then you can do prediction. In other words, I give you a new number, say for example 3, and then you will be able to tell me that the output is a 2.71. Okay? So again, as we discussed last time, we are not interested only in the outputs of the training sample, because if these are the only samples that you are interested in, then you don't really need a machine learning model. All you need is a database. Okay, if you have a database, then you can ask me what is the output when x is equal to 2. Okay, then the database will tell you it is 3. But however, if you ask the database what is the output when x is equal to 3, then the database will say record not found, right? Okay, because there is no x equals to 3 here. So this is the difference between database and machine learning. Okay, so we want to have predictive power. Okay, you show me new inputs, I will be able to answer and tell you the corresponding output. Okay, so diagrammatically, so this is what we have. We have the 3 inputs, the 3 dots here. So this is the input, this is the corresponding output. So you want to learn the underlying trend between the input and output. So of course, so here we talk about linear regression. So in this case, linear regression means that you want to fit the points by using a straight line. Okay, so this is one possible line you can fit. Okay, so that means that in a regression problem, so first of all you have to decide several things. The first thing is which predictor to use. Okay, so you have to define the hypothesis class. So for linear models, so obviously the class, so this line is one possible model in my class. Okay, but obviously this is not the only straight line that you can use, right? Say for example, you can use, what other straight line you can use? You can use this straight line. Okay, you can use this one, okay. So in fact, there are infinite number of straight lines you can use, but all these are straight lines. Okay, so this is what we meant by hypothesis class or model class. Okay, this is a class of models. Okay, so this is not one single model, this is a class of models. So obviously in this example, so obviously you are given the 3 points, and then now you use this particular red line. So is this line good or bad? you want to capture the underlying relationship between x and y, so you use this red line. Is this good or bad? Bad. Okay, so the three dots doesn't seem to suggest this downward trend. Okay, but then of course, well, if this is bad, then what about this? This is also bad, right? So the point is that you have to tell me how bad or how good a line is. Okay, so that means that you have to somehow be able to evaluate the model. Okay, and so that leads to the second thing, that is you have to define a loss function. Okay, so somehow you have to score, you have to measure the performance of this particular model. Okay, so we will go into the details, and then of course after that, suppose that you have a loss function. Okay, you somehow tell me that for this red line it is not good. Okay, you give me a score or a loss. Say for example it is a loss is 100, say for example. Okay, so the loss is big. So what do you do? So recall that you have a model class, so you have a lot of stress lines that you can choose from, and then each stress line will have the corresponding loss value, and so the goal is to find the stress line that, so you have the class of stress lines, you have a loss function to measure the performance of the stress lines, and then you want to find, the goal is to find the line that minimizes the loss. Okay, so you want to minimize the loss, so that means that leads to the third question. So you need some optimization effort. Okay, so in regression setting, you need to define the model class, you need to define the loss, you need to find optimization algorithm. Is it clear? So let's go into the specifics. So as I said, so we are talking about linear models. So we have, in this case, one single input, okay, and one single output. And so this is a stress line. So the equation of a stress line like this is of the form y is equal to, so what is the equation of a stress line? Yeah, ax plus b, right? Or mx plus c or whatever. Okay, so basically, so it is something like this. So usually we have a name. Say for example, this number is called the what of the line. Slope, and then this one is the intercept. Okay, so the slope basically controls the angle, okay, and the intercept controls the shifting up and down of the line. Okay, so in this case, you specify the slope and intercept, or you change the slope and intercept. So say for example, well, you change this to this, and then you will get a different line. Okay, so more generally, that means that you have the two parameters, W1, W2. Okay, you can vary this, and then you will get an infinite number of lines. Okay, so this is the model class or hypothesis class. Okay, so in that means, what that means is that you have a family of models. Okay, so this is parameterized by W. Okay, in W, in this case, W contains the two parameters, W1, W2. So usually in machine learning, we prefer a more complex notation, so using a vector. Okay, so this is a two-dimensional vector or weight vector. So you have W, and then if you define phi x like this, okay, this is another two-dimensional vector. Then if you want to produce a W1 plus W2x, then what you can do is to simply take the dot products of this W and this phi x. Okay, so this is the dot. So this dot denotes the dot product. So anybody who doesn't know what is a dot product? So everybody knows what is a vector, right? Okay, good. So in this case, okay, so you have, this is the model, okay? And then by varying W, okay, you can get all the different stress lines. So in other words, in this case, so this is the model class or hypothesis class. Yeah, this is the hypothesis class. Okay, and then this class of models, well, is obtained by varying the W. So the W is a two-dimensional vector. Is it clear? So this is the first question, okay, the model class. And then once I have the model class, the second thing I have to look at is the, as we said, the second thing is the, so first you have to define the hypothesis class, okay, which models, what kind of models you want to use. And then the next thing is you want to specify the loss function, okay. So say for example, you have to tell me whether this red line is good or bad. Okay, so how to do this? So again, so recall that this is what we have. So we have the 3 dots. Okay, so this is the training samples. And then this is your model. Okay, so obviously it is not good. So we have to measure how good or how bad it is. Okay, loss function, so measures how bad it is. Okay, so how bad it is. So it is good if it can, so say for example, pass through all the green dots, then it is good. But however, this is bad. So say for example, when x is equal to 1, so when x is equal to 1, okay, so you look at the model, okay, then the model will give you the corresponding y is a 3 point something. Okay, but however, as you can see from the training sample, so when x is equal to 1, the y should be equal to 1. Okay, so your prediction is very far away from the output. So what should we do? So how to measure the performance? So very simple, right? So you just measure the gap. Right? You just measure this gap. Okay, and so similarly for the second point, this one, that point, this one. Okay, so in other words, so you just measure the difference between the model prediction at x and the corresponding y, okay, from the training sample. But oftentimes we also do a square. So why? So all of you, I guess 99% of you have taken one or more than one machine learning class, right? So why do we need to have a square here? Yeah, because we have minus. You can have plus and minus. Okay, so say for example you are 2 meters tall. I think you are only 1 meter tall, then I'm wrong. But if I think you are 3 meters tall, again I'm wrong. Okay, so whether I over predict or under predict, it doesn't really matter, right? So plus error is as bad as a minus error. So we want to remove the sign. So the easiest way to remove the sign is to take the square. Okay, so that's why this is called the square loss. Of course, you can argue that, well, I don't like to take the square. I can also do absolute value. So if you want to remove the sign, you can also do absolute value. Okay, so this is another commonly used loss function. So here we stick to the square loss. Okay, so once you define the square loss, then I give you any weight factor. So this is the W that we have on the previous slide. Okay, so for this particular W, okay, you obtain the line, and then for each, recall that we have 3 training samples. Okay, so for each sample, you can obtain the corresponding loss value. Okay, so say for example, so this is the W times the X, okay, and then minus the Y squared. So for the first part, the square loss is 0.32, and so on and so on. Okay, and so of course, so you have 3 training samples. So the training loss, okay, has to sum over all the samples, okay, in the training set. Okay, so you can just use the sum, or if you want, you can also do the average. So it doesn't really matter, because at the end, what we want to do is to find the W that, so in fact, at the next step, what we want to do is to find the W that minimizes the loss. Okay, so here we sum over all the samples. Okay, if you do the average, that will be the same because the W that minimizes the sum will also minimize the average, right? So this is just a constant. So anyway, so using the average may make the number smaller, okay, and more interpretable. So this is the second part, okay, the loss function. So you know how to measure the performance of a predictor. So the third part is on optimization. Okay, so what optimization? Again, as I said, so you have the loss function here. So you can plug in any W. Okay, you vary the W, then you will get a different line. Okay, different line will give you different predictions, and so will give you different loss. Okay, so diagrammatically, in our example, we only have two parameters in the weight vector, okay, W1, W2. So that means that if you, for example, so this is the W1, W2 space, okay, or the weight space. So you can say, for example, pick this particular W1, W2, and then plug into this equation, and then you can obtain the corresponding loss. So say, for example, at this point, the loss will be here. So the y-axis, or the z-axis, okay, is the loss. So this is here. And if you pick a difference W, say, for example, this one, the loss will be smaller, and so on, so on. Okay? And so, of course, as we said, so we want to find the weight combination that minimizes the loss. So that means that we want to find this point. Okay? So this is why we want to do optimization. Any questions? So you should have learned all this before, right? No? So how many of you have taken machine learning course and have never learned something like this before? Okay, interesting. Okay. So anyway, so this is the loss function. Okay. Because for supervised learning, so typically you have to define the loss, right? Okay. So anyway, so you have the model class. Okay, you specify what models you want to use, and then you know how to measure the performance of your model. Okay, and then you want to find the best model. Okay, so this is optimization. So this is the loss. So W is the unknown. Okay, so this is the optimization objective. So basically, this is just an optimization problem. Okay, and so you can, in principle, use whatever optimization problem that you know. Okay, so I suppose some of you are from the math department. Anybody whose undergrad is in math? No. So anyway, so there are lots of optimization algorithms, but in this course or in machine learning, so the most commonly used optimization algorithm is based on the very simple gradient descent. Okay. So what is gradient descent? So what is the gradient? Okay. The gradient is basically the slope. Okay, or the derivative. Okay. So the notation is this one. Okay, so this is the objective. Okay, so this is a function of W, and then this is the notation. Okay, so when this W is just a scalar, okay, one-dimensional. So this is basically d by dx, right? Okay, so in your high school, okay, mathematics, so this is what you have. Okay, you have a function f, which is a variable, which is a function of y, which is a function of x, and then x is just a scalar, okay, and then you take the derivative. This is the gradient. So here it is just a little bit more complicated in the sense that, so what's the difference with this? So this W is typically a vector, okay, because the number of parameters in the model is often, well, quite large. Okay, so even in our simple example, we already have two parameters. Okay, so W is a vector. So this is the notation. Okay, but you can always, oftentimes you can just kind of connect this with your univariate calculus. Okay, the rules are very similar. So now this is the gradient. So the gradient basically gives you the direction that increases this objective the most. Okay, in other words, so if you stay, for example, start from here, okay, you start from here, then the gradients will tell you what? The gradients will tell you how to increase the loss. Okay, but however, in our problem here, so we do not want to increase the loss, we want to minimize the loss. Okay, so that's why instead of going, so if the gradient tells you to go in this direction, okay, which will increase the loss the most, so you don't want to do this. You want to go in, so in the opposite direction, right? So that's why you have you want to do gradient descent, okay, instead of gradient ascent. So the gradient descent algorithm is very simple. So basically, what you have to do is that, well, this is an iterative algorithm. Okay, so first of all, you have to start from somewhere. Okay, so here we use all zero, but oftentimes in practice, we don't start from all zero. Anyway, the point is that you start from somewhere. Okay, and then this is an iterative algorithm, so it performs a number of steps, iterations. Okay, so say for example, big T iterations. So in each iteration, what do? You start from this W, okay, and then you want to make some small change, okay. So this is the gradient, and then you want to do descent, okay. You want to reduce the loss, and so you have the minus sign here, okay. You want to go into the opposite direction, and then besides you have this eta, which is the step size, because if you want to go in this direction, okay, you can take a very big step. You can also take a very small step. Okay, so eta basically tells you what is the step size. And then you use this to change your current W, and then that becomes your new W. Okay? And now, after obtaining the new W, you just repeat the process. Okay? So, diagrammatically, that means that you may start from here, okay, and then the corresponding loss is very high, okay, and then you do descent, okay, you may go to a little point here, and then the loss is smaller, another point here, and so on, so on, so on, okay, until, well, you perform a large number of steps, so hopefully at the end you will end up somewhere here. So, how many of you have heard of gradient descent? Good, okay. So, of course, for gradient descent, as I said, gradients basically means derivative, okay? And so, this is the objective, okay? So we want to compute the gradients of this, and so we have to do differentiation. So how many of you don't know differentiation? Good, okay. So we just do differentiation. So as you can see from here, so we have to differentiate this thing. Okay, and so that means that on the right hand side we have to do this. Okay, and then what? And then of course this one is a constant, and so we can move this differential operator inside, right, to become this. And then this is differentiates a summation of functions, and so this is equal to, so you can again move this differential operator inside, and so this becomes this. Okay, and so now you have to do this, and somehow your undergrad math course should have told you how to do this. Okay, again, so you just take, so the difference is that this is a multivariate calculus, okay, but then basically it is very similar. So you have the square, and then you have the 2, okay, and then this is from here, okay, and then you have this, which is from here, okay. So here I assume that you know how to do differentiation, okay, basic differentiation, okay, and so, well, from the objective you can obtain this is the gradient, okay. So of course everything is known, So W is the current W, phi x is, as I said, the vector, two-dimensional vector, 1x. And then Y is from the training set. This one is again from the training set and so on. So everything is known. So in each iteration, you can compute this one and then update W by using this equation. Okay? So here's a kind of more detailed example. So, but I guess I don't need to go through this, right? Because everybody knows gradient descent. Okay, so basically this is our example. So in summary, so if you want to do regression problem, so first of all, this is a supervised learning, so you need to have a training set, okay, with both the input x and the output y, okay, and then before you do regression, first of all, you have to think about what models to use, so you have to specify the hypothesis class, and then so here we have the class of linear functions. And next, you have to somehow measure the performance of the model, so you have to specify a loss function. So here we use the square loss. And then finally, you have to pick an optimization algorithm so that you can find the W, which minimizes the loss. Okay, and here we use gradient descent. Is it clear? So pretty simple, right? So this should be just a revision, I guess, for 99% of you. Any questions? No? So this is a regression. So what about classification? So for classification, again, so this is very similar. Recall that's the only difference between classification and regression is that so you still have x, y, okay? You still want to learn the mapping between x and y. So the only difference is that for regression, the y is a number, and whereas for classification problem, the y is a label. Okay, so an example is like this. So here, again, you have the training set. So here still we have 3 samples. So here we assume that you have a 2-dimensional input, okay, x1, x2. So for the first part, 0, 2, corresponding label, output label is 1, and then this second one is also 1, third one is -1. Okay, again, this is a binary classification problem. Okay, so the idea is very much the same. You have a training set, you want to go through some algorithm, and then you want to obtain a model. Okay, so since we are talking about a classification problem, so the model, well, in this case, it's called the classifier. Okay, for the regression problem, the model is called so this is a classifier. So in the previous case, the model is called regressor. Okay, so anyway, so classifier, regressor. But then the operation is basically the same. So once you have this model, then I can give you a new input, 2, 0. So note that 2, 0 is not in the training set. Okay, so this is a new sample. But still, once you have the model, you should be able to classify or make a prediction on this sample, say for example -1. Okay, so diagrammatically, again, it is very similar to what we have before, except that recall that now we have 2-dimensional input. Okay, so x1, x2. Okay, so each point is a 2-dimensional point. So we have 2 classes. Okay, so here we denote by the color yellow and blue, yellow and blue. Is it one? Yeah, yellow and blue. Okay, yellow and blue, and then we want to build a classifier, right? So that means that we want to separate this input space into 2 parts. Okay, one is for the positive class, the other is for the negative class. So again, so I suppose everybody has learned this, so maybe I move a bit faster. Okay, so if you don't know what I'm talking about or you want me to go slower, please let me know. Otherwise, I will move faster. Okay? So this is a classification problem. And so this line, of course, is called the decision boundary. And since we are talking about linear models, so the boundary is a line. So this is for 2-dimensional inputs, then it's a line. If I have 3-dimensional inputs, then the boundary is a So this is x1, x2, right? So more generally, you can have 3 inputs. Okay, x1, x2, x3. You can still have a linear boundary. So the boundary is a plane. Okay, more generally, if you have high dimensional input, then the boundary is called a hyperplane. Okay? So still we have to answer the 3 questions like before. So first of all, what models are used? So here, as I said, so we want to use linear models. Okay, so this is the model class or hypothesis class. Okay, the second question is, again, so you have to tell me whether this model is good or bad. Okay, so we use, again, you have to define a loss function. Then thirdly, so obviously I want to find a model which minimizes the loss. So again, I have to use an optimization algorithm. Okay? So we want to use a linear model. Okay? So linear classifier. So again, we have seen something like this. Okay, so this is the feature, x1, x2. Okay, and then here this is the weight parameter. Okay, w1, w2. And then I perform the dot product. And then now since I do classification, I add a sign function here. Okay, the sign function basically turns this value into +1 or -1. Okay, since you have 2 classes. So in the exceptional case when this one is exactly equal to 0, so it depends on how you define it. Okay, so here we assume that this is equal to 0. Okay, but more generally, okay, so we basically partition it into 2 classes. So you are given the training set, okay, and then if you have this is your current model parameter, then you get this boundary, okay, and so now you have this W. So I give you any x, you can just plug into this equation and then obtain the corresponding class labels, right? And so, say for example, so and then by taking the sign, then you will see that for points lying on this side, maybe so the sign is equal to +1, okay. And then for points on this side, the sign will be equal to -1, okay. And so what about the points that lie exactly on this line? So the value of this will be equal to what? So what that means is, okay, you look at the dot product, right? And then look at the sign of the dot product. And then use the sign to put the points into plus class and minus class. Okay, so here, suppose that the dot product is positive, so you put it in the plus class. Here, the dot product is negative, so you put that in the negative class. So what if the point lies exactly on this boundary? So the dot products will be equal to 0, okay? So obviously 0, okay? So that's why for the decision boundary, okay, so the dot product is exactly 0. Okay? So again, so this is the model class that we're using. Okay, so the functional form of the model is dot product and then sign. Okay, and again, just like in the linear regression case, you can vary W. So W in this case is again the 2-dimensional vector. So you vary W, and then you can obtain a different boundary. Okay, and so you can try all different W's, and so this gives you the hypothesis class. Any questions? So now, obviously, not all boundaries are equal. Some are better, some are worse. So that's why you again need to use a loss function to tell me how good is a particular model or classifier. So, how to measure the performance? So this is a bit, yeah. So this is a PowerPoint problem. So maybe go back to this picture. So recall that. So this is the training sample. Okay. So when x is equal to 0, 2, well, the training set says that the correct label is 1, and so on and so on. And then you can look at this. Say, for example, 0, 2 is, this is 0, 2 is here, okay? And so, say the model predicts plus class, and so the model is correct or incorrect? Correct. And so what should be the corresponding loss? So just like in your final exam, okay, there will be a number of questions, and if your answer is the same as the model answer, then you will get a penalty of 0, obviously, right? If I deduct your marks, then you will be unhappy. Agree? So when your answer is correct, of course you don't have any penalty. Okay, so this is the case for this point. And so you can look at the second point, -2 and 0. Okay, so the training set label is y, but the prediction is -1, and so the prediction is wrong. Okay, so you will have a penalty. So how much penalty? So whatever penalty, but anyway, this is a mistake. Okay, so basically you have 3 samples, so intuitively, well, I can measure the performance of this classifier by counting how many mistakes. Okay, so now this is right, this is wrong, and maybe this one is right, and so on. Okay, so that's why we can use something called the 0-1 loss. Okay, so what is this? So basically, for a particular sample xy, I look at my prediction, okay, by using the model with parameter w, and then I look at the training set label. If they do not agree, okay, then this is true. Okay, and what is this one? This one is the so-called indicator function. So this indicator function will return a 1 when the input argument is true. Okay, in other words, when your prediction disagrees with the training set label, then this will output a 1. So essentially, it says that, okay, you have committed a mistake. Okay, so otherwise, when your prediction is the same as y, then this argument is false, and this indicator function will return 0. Okay, so that's why it is called a 0-1 loss. Very simple and intuitive. Agree? So similarly, you can look at, well, the 3 samples, okay, run through the equation of the model, okay, and then see whether this dot product, the sign of this dot product agrees with the training set labels, okay, and then you will see that it commits 1 mistake. Okay, so according to the 0-1 loss, so the loss over this whole training set is equal to 1, or you take the average, will be 0.33. Is it clear? So this is how you can measure the performance of a model, a classifier. So we have specified the hypothesis class, we have specified the loss function, so what's next? Huh? Yeah, so somehow, well, again, so not all boundaries are equal. Okay, some are good, some are better. Okay, so now I have a way to measure how good or how bad each boundary is, and so the next step is I want to find the W, okay, that can give me the smallest training loss. Is it clear? Before we move on to that, maybe we take a break. Okay, so maybe 10 to 15 minutes. Okay?
无忧，我感觉就是属于他知道自己很漂亮，然后很美，所以他就不谈恋爱，或者是找那种比较屌的，然后谈对象。然后我感觉可能，因为他和他另外一个人，说实话，经济有点差。他经济有点，我不知道，我这边有一个东西是其他的。但说实话，他这个建模的，然后他是，卓越哪个人是不是？他是我就整天吃我所以我在那边说，我好自卑啊！真的，我很难想象有一个，我这样搞，真的确实。然后当时我大一的时候，你们还在北京，你有个72人，我知道，他这人挂过来，对，政治，他们之前给我怀疑过我哎，你就直说吧，你是不是就无忧我帮助我为什么觉得我要找？因为我一来不是这些跟是很活的，我没有微信都没有，我跟他没有什么，我跟他没有同事，就是做活动，对啊。我大一的时候，我都没在北京。大一的时候没，后来就开始看。在北京，你别告诉你在北师才。但是他们当时说我们做个无忧，在搞对象，我所以我要是谈一个这样的，我还搞对象。对啊，我无忧谈谈。真北邮，北邮第一社长。当时媒体的同学都知道了，都知道北邮有一个北邮。所有视频都让他做一次，就无忧那，对啊。然后还有一个今天视频，说我当时。最容易的。哦，四川的，也是川的，我知道那个四川的，也是拍那个学校的照片，他抖音的粉丝关注挺多的，王志远，我这边，你们这边学妹我不认识，你给点是不行，给点关键词，你给点关键词，我能查不少，给点关键词。我操！我这帮真不认识。你看我20岁了，他说我刘总，是这个什么？说的就是他，是他的。你看他照片，我不见过，但我知道我看一下。
So okay, so let's continue. Okay, so we were talking about linear classifiers. Okay, so in particular we talk about linear classifier. Okay, so linear classifier. So again, recall that. So this is the model, okay, that we're using. So W is the model parameter, and Then, so for a particular model, okay, so we measure the loss on a particular XY sample, okay, by using this 0-1 loss. Okay, so basically, we are trying to see if the model makes any mistake on this particular sample. Okay, so if you are correct, then the loss is 0. If you are not correct, then the loss is 1. Okay, so essentially, by looking at the whole training set, that will be the total number of mistakes that you make. Okay, so obviously, we want to find the W, okay, such that the total number of mistakes is the smallest, okay, or ideally equal to 0. So that's why we did optimization problem, optimization algorithm, okay. So before we move on, so optimization algorithm, so for the regression case, we use gradient descent. Okay, so obviously we said that the gradient descent has been very commonly used in today's machine learning algorithms, particularly deep learning. So obviously we still want to use the gradient descent. But before we move on to talk about the gradient descent, so first of all, so let's look at this function. Okay, a bit more detail. Okay, so first of all, so recall that. So what we want to do is that for a particular input x, so a particular x, okay. So what you want to do is to first do the dot product, okay, and then take the sign, right? So and moreover, as discussed, so what this linear classifier is doing is that it will separate the input space into two parts, the plus region and the minus region. Okay, so essentially what we are doing is we take the dot product and then turn that into a sign. If the dot product is positive, it will be here. If the dot product is negative, it will be here. In other words, if I have points here, okay, then the dot product will be positive. If the dot point is here, the dot product will be negative. But we can also see that so what's the difference between, say, a point here and a point there? Okay, so for both points, so at this point and this point, their dot products will be positive. Okay, but then can we say something more about the two dot products? So we expect, say, the dot products for this green point to be bigger than the dot products for this one. Okay, so say for example, this may be plus 10, this may be plus 0.1. Okay, so similarly, if the point is here, okay, maybe just again use the blue. If the point is here, okay, if the point is here, okay, compare with another point here, okay, then the dot products for this point may be, so will be positive or negative. Negative, say this one may be -1, okay, and this one may be -5. Okay, so basically the dot product tells you how confident, okay, the model is in predicting the points to be +1. Okay, so if it is very positive, then intuitively the model thinks it is very positive, very likely to be from the plus class. Okay, so we call this the score. But however, you are confident doesn't mean that you are right, right? So in your final exam, okay, you think the answer should be yes, suppose there is a multiple choice, okay? Or suppose there's a true-false question, okay? And you think the answer is yes, but you may be wrong. Okay, it's the same for this classifier. So you can have a very big dot product, but you may be wrong. But we can also consider this, okay, if we also multiply this by y. So what will happen? So if you think it is very positive, okay, the dot product is very big, positive, and then you are correct, then in that case, that sample, the y should be equal to 1. Okay, plus 1. And so this whole thing will be, so suppose the dot product is plus 100, and then you think it belongs to the plus class, and it really belongs to the plus class, the y is equal to 1. And so this product will be equal to plus 100. Okay. And so similarly, you think it is very likely that it comes from the minus class. So this number, the dot products can be, say, minus 200. Okay. And then if that's the case, and if you are right, then the y will be equal to minus 1. And so this product will be equal to 200. Okay, so anyway, so that means that if this number is very big, okay, then that means that you are very correct. Okay, and so sometimes we call this the margin. But whereas, say for example, you are very confident that this belongs to the plus class, so this is 100, but then you are wrong. So this number will become, so you think it is 100, but in fact you are wrong. So that means that the true y will be equal to minus 1, and so this is equal to minus 100. So again, that means that the margin will be negative. And so similarly, when you think this is a very negative 200, okay, but then in fact you're wrong. So the y is actually plus 1, and so this whole thing is minus 200. Okay, so what that means is that the margin can tell you how correct you are. Okay, and then it can be easily seen that, so this is the 0-1 loss that we talked about earlier. In fact, it can be rewritten like this. Okay, basically it is the margin, and then compare with 0, and then the indicator function. Okay, or we can simply use this diagram. So as I said, so if the margin is a positive, that means that you are confident, and then you are right. Okay, so here, this region. Okay, and you are right, you are correct, so that means that of course the loss should be equal to 0. Okay, in the final exam, you answered the question correctly, so the loss is 0. Whereas if the margin is negative, okay, that means that you are not correct, and so the loss will be equal to 1. Okay, so this is basically the 0-1 loss. And so as I said, so for any given W, okay, so you can then measure the loss. Okay, so of course this is the loss over one sample, and then you have to aggregate the loss over all the training samples. So that will give you the performance of this linear classifier with this particular W on the training set. And as we said many times before, so not all models are equal. Okay, so some models are better than others. So basically, what I want to do is to find the W that can give me the smallest loss. Okay, and so we have to do optimization. Okay, and again, as I said, optimization, we just want to borrow techniques from the regression case, and so we want to use the method of gradient descent. Okay, so again, what is gradient descent? So again, this is what we want to do. We have a loss, which is a function of the W, the weight parameter, and so I want to minimize this loss with respect to W. And I want to compute the gradient. Use gradient descent. Okay, gradient descent, of course, you have to compute the gradient, and then again, as we said before, this is just the derivative. Okay, so this is the derivative of this function, and so now for classification problem, you just plug in the 0-1 loss, which is this one. Okay, and then you have the differential operator. Okay, so again, this is a constant, this is a summation, so you can move the differential operator inside, and so that gives you this expression. Okay, so now, so you have to, well, this is summation, this is division, so simple. So the most complicated part is, of course, to compute the gradient. This one. Okay, so what is this? So recall that we have the 0-1 loss, and equivalently on the previous slide, you can also write it this way. Okay, and so when you look at the gradient, so recall the diagram. So this is the loss. Okay, you want to compute the gradient. Gradient is just a derivative. Okay, so the derivative of this is equal to what? So obviously, here it is flat, so the gradient is 0. Here it is flat, gradient is 0. Okay, only when you are at this point, you will get non-zero gradient. But this point occurs, there's only one point on the whole real line. Okay, so this is very rare. So what that means is that most of the time, you get 0 gradient. So if you get 0 gradient, then what will happen? You want to do gradient descent. Okay, so recall that gradient is that you have a direction that you want to update, you want to move in this direction. And when the gradient is 0, that means that there is no update. No update means that the new W is the same as the old W. Okay, so W0 is the same as W1, is the same as W2, and so that means that you are not learning. Okay? So that's the problem with the 0, 1 loss. Okay, gradient is 0, so basically you're not moving at all. Agree? So that's why typically we don't use the gradient, or we don't use the 0, 1 loss. Okay? If you want to do gradient descent, you better use some other loss. So what loss can we do? So the 0, 1 loss corresponds to this curve. Okay, and then the problem, as we said, is that it is basically 0 all the time. So what can we do? So there are many ways you can fix it. So one thing is that, okay, maybe instead of using this, I just replace this by the green curve. Okay, so what does the green curve tell you? So first of all, so again, this is the margin. Okay, so this is the margin in this part. So basically, what does that mean? So the margin is positive. Okay, recall that margin is positive. What does that mean? That means that you are correct, right? You are correct. You are correct. Okay, then that's good. In fact, well, maybe we look at the negative part. Okay, you are in the negative part. That means that you are incorrect. You are not correct. Then what should you do? Of course, you need to change, right? So if you fail so recall that in this course, the grading scheme consists of what do you need to do? So we have nothing, all pass. Is it? No, so we have a final exam, right? So before the final exam, we have nothing. So we have something, right? So we have a quiz, okay, anyway. So we have a quiz, okay, so basically a midterm, okay. So suppose that in the midterm, okay, so of course, if in the midterm you get 99 marks out of 100, so what does that mean? You are doing very well, right? So if you were this linear classifier, then basically your margin will be, where will be your margin? So you are doing very well, so you are kind of correct. Okay, so if you are correct, so what should you do? You don't need to do anything, right? You don't need to change. Okay, you are doing well, very well. But however, if you only get 10 marks out of 100, so what does that mean? That means that you have to change quite a lot, right? So this is essentially what this is saying. If the margin is negative, you are not correct. Okay, you have a loss. Okay, so you have a loss. So here, I use the green curve. So in the 0, 1 loss, okay, no matter whether you are, how wrong you are, okay, so in this part you are all wrong, okay, but no matter whether you are a little bit wrong or very wrong, you get a penalty of 1, okay? But for the green curve, what it says is that if you are a little bit wrong, you have a penalty. If you are very wrong, you get a very big penalty. Okay, so that kind of gives you more incentive to change, right? So suppose that the passing mark is 50. Okay, you are 49. You got 49, that means that you need to change. But a little bit, maybe. Okay, if you want to pass. But if you only got 1 mark in the quiz, then, of course, yes, Oh, okay, yeah. Okay, so we are still talking about this part first. Okay, so here in this part you are wrong. Okay, you're wrong, and then you have to change. And you are very wrong, then the loss is higher. Okay, when you are just a little bit wrong, your penalty is smaller. Okay, and then for this part, okay, if you talk about 1 to 3, then basically you are correct. Okay, you are correct, and so you don't need to change. Okay, makes sense. And then previously we say that when you are here, okay, in fact, whenever the margin is positive, that is greater than 0, then in fact you are correct. Okay, you are correct. And in fact, for this part, you don't need to change, right? But then here, you have this hinge loss. Okay, we have this green curve, and then so we have this part basically. So we have this part, right? And then we have this part. Okay, so now, what is this? Right, we have this. So what is this? Okay, so of course you can argue that well, this should be 0. Okay, but what the hinge loss does is that, well, first of all, is simplicity. Okay, partially, so that we have this 2 straight lines. Okay, and then the other thing is that, okay, what does that mean when you are here? Okay, again, suppose that it is the midterm. Okay, you get 51 marks. You pass. Okay, do you want to change? You still want to change, right? You are lucky this time, 51. Okay, or 15.1 marks. Okay, you got 15.1 mark. You passed the midterm, but still, you probably want to change. So that's why essentially he's doing something here. Yeah.
Just a question. If anyway we're trying to minimize loss, wouldn't it be best if you maximize the margin as much as possible? So say for example, shouldn't loss say be 0?
Yeah. So maximizing the margin is what we will talk about. What we will talk about is the support vector machine. Okay, yeah. So here, this is just a linear classifier. Okay, simplest model. Okay, so yeah, you are right.
But even with the linear classifier part,
Yeah. So again, so the point is that what we are trying to say here is that the 0, 1 loss is very intuitive. Okay, you are right, 0 loss. You are wrong, loss 1. Okay, so this is very intuitive, but then this is not good for gradient descent. Okay, so if you want to use gradient descent, you have to change the loss a little bit. So there are many ways of changing the loss. Okay, so hinge loss is just one of the ways that you can use. Okay, so you can use many other losses that you like. Okay, so just like for the regression case, the simplest case is you use the square loss. You don't like the square loss, so I'm not saying that the square loss is the best. Okay, you can use some of the losses. Okay, you can use the, as I said, you can use the absolute value, which is what we call the L1 loss. Okay, you can use many other losses. Okay, but then these are the kind of most simple losses. Okay, so again, hinge loss, well, not the best. Okay, but this is a kind of a straightforward modification of the loss. And so what I want to say is that we want to have non-zero loss in this region is because you are only marginally correct. Okay, so we still want to give you a penalty so that you will change. Okay? So this is, and then mathematically, so the equation of this hinge loss is given by this one. So of course, you can use some of the loss. Say if you have done some statistics, okay, and then you have the logistic regression, and the logistic regression uses the logistic loss, and this is the equation of the logistic loss. Or better look at the diagram. Okay, so this is the yellow curve. So red curve is the 0, 1 loss, green curve is the hinge loss, and then you can see that's where the logistic loss basically follows the same idea. Okay, in this part you are wrong. Okay, and so you have non-zero loss, and then you are very wrong, you get a higher loss. Okay, you are just a little bit wrong, you get a smaller loss. And then when you are here, you are very correct, you have 0 loss. Okay, and then here, well, you are quite correct, but then you are just marginally correct. Okay, so I still give you some loss. Okay, and then the logistic loss is smooth. Okay, the hinge loss is not smooth. Okay, there is a point of discontinuity here, whereas the logistic loss is this. Okay, so of course, in classification problem, so you can also use many other losses. Okay, so these are some some examples that you can use. So and then say, for example, if you want to use the hinge loss, okay, then this is the hinge loss, and then you just compute the corresponding, do the derivative, okay, do the differentiation, and then intuitively you can see that's when this part, okay, so recall that's, so basically you're here, okay, then you have some loss, okay, whereas when you're here, you have 0 gradients. Okay, so the point is that now, so the difference, the key difference with the 0-1 loss is that 0-1 loss you almost have 0 gradients all the time, and so you don't know how to update. But whereas here, okay, when you are here, you have non-zero gradients, and so you try to update. Okay, and of course, similarly, you can use the logistic loss. And here's again an example. Probably I don't need to go through the numerical example here, right? So it's just you have the loss, okay, and then you have the different samples, and then if you use this particular weight configuration, and then these are the corresponding weight values, and then you plug in the equation of the gradients on the previous slide, and then you get these 3 gradients. Okay, in particular, you see that when there's a 0, okay, then the loss here can be 0. And so the total loss over the whole training set is just add all these together, okay, and take the average. And then the gradients is just, again, add all of these together. And so you do the updates by applying this gradients update equation, so W minus eta and then the gradient. Okay, so that will become the next W estimate, and then you repeat the process. Okay? So in summary, so this is about supervised learning, the simplest model, linear model. So we talk about regression, classification. So since this is linear model, so basically the crux of the model is of this form: the W parameter vector, dot product, the feature vector. Okay, and then recall that if you are talking about the regression, then you just output this dot product. If you want to do classification, you want to turn this into class labels. Okay, you can put in a sign function here, and then you have to so this is the model class. Okay, and then we have to define the loss. So for the regression, you can use square loss. Okay, you can also use the L1 loss, as I said. You can use other losses if you like. And for classification, you can use, we talk about 0-1 loss, hinge loss, logistic loss. Okay, and then for the optimization algorithm, well, in this course, at least, okay, we use the gradient descent. Any questions? Okay, so next. So next, well, so up to this point, we talk about that you have the training set, okay, and then you want to do supervised learning, regression, classification. You learn a model, okay, and then you have some parameters associated with the model, okay, and then you want to find a model which minimizes the training loss. Okay, so now is this the best? So let's look at an example. So here we have 2 classes, again, binary classification problem. So we have the circles and squares. And of course, so you can see that if you use the linear model, linear classifier, so here we have a 2-dimensional input. Okay, if you use linear model, so what will happen? So maybe you will get this classifier A. Okay, so obviously, well, it may not look very good. Agree? So it cannot perfectly separate the 2 classes. And so in general, linear models are not good enough, right? Because in the real world, oftentimes the 2 classes can be very complicated. So say, for example, if you do 2 classes like this, okay, then obviously you cannot use a linear model, because then the best you can do is this one, and then you will have a lot of errors. Okay, so this is typically what we have here for model A. And so if a linear model is not good enough, then what can you do? So you can use a nonlinear model, right? So of course you can use a very complicated nonlinear model, but then nonlinear, well, also means a lot of variety, okay? So say for example, you don't like model A, then maybe you can use something which is just slightly more complicated than a linear model. So in this case, this is a kind of like quadratic decision boundary. Okay, so you can use this boundary, and then you will try to, again, quadratic. That means that you will have some parameters associated with this quadratic classifier. Okay, and then again, just like before, you try to learn the parameters of this quadratic classifier. And so suppose that what you learn is this model B. Okay, and of course, if you like, you can also use a very complicated model, okay, with lots and lots of parameters, okay, and then you may be able to fit the boundary, which is this model C. Okay, so now the question is, so which model is the best? A, B, or C? So how many of you think A is the best? B, C? So most of you pick B, so why B is the best? I would argue that, so this is the data set, okay, so again, I can measure the training loss, just like what we did before, okay, so what is the training loss? That is, say for example, I just count, so how do you measure the performance at the end? So you use whatever loss in the training, okay, but then at the end, when you want to measure the performance in a classification problem, you measure the performance by basically counting how many mistakes you make. Okay, so of course, if you use model A, you can see that it makes a lot of mistakes. So this part is the blue part, this part is the red part, but then you can see that all these points will be classified as red. Okay, and then these points will be classified as blue. So the model A obviously is not very good. For model B, is it good? It is much better than the linear model, but then you can still see that this point, say for example, will be classified as blue, right? And this is also blue, and then this one will be classified as red. Okay, but whereas for the model C, so you can see that it perfectly fits all the points. So the error here is equal to 0. Agree? So why is model C not the best? Yeah, so the point is, so this is only on the training set. Okay, so again, as I said, so are we just interested in the training set? No, because if you are only interested in the training set labels, then you better use database. Okay, database, it will be perfect. Okay, you do a query, and then it will give you, if you just look at the database, look at the data set, okay, and they give you what's reported in the training set. And for machine learning, so we are more interested in unseen samples, which means that if I give you a new point, I want you to predict whether this is red or blue. Okay, so what's the problem? So that means that if you look at the training loss or training error, okay, if we are talking about a classification problem, so just like before, you have the ground truth. So here we use F, okay, so the notations are a bit different, okay. So suppose that the target function, the underlying function is F, and we have a hypothesis, okay, H. And then this hypothesis, well, before the break, is a linear model, okay, and then of course in practice, so you may want to use, say, neural networks. And then, just like before, you have a training set, okay, but then this training set, obviously, will not cover all the possible samples. Okay, so say for example, if I want to do face recognition, I want to see whether this face is male or female. Okay, so I can use all the face images here in this class to construct my training set. But obviously, does this population or does this sample include all possible face images? So of course not. So there are lots of face images outside this room. Okay, so after looking at all these face images, I want to build a classifier so that well, when I go outside, I look at new face, I can make prediction on whether this is male or female. Okay, so you are only given a training set, which is a subset, okay, which is drawn from some underlying distribution. Okay, and so the training error, as we said, is just the misclassification error that I make on this training set S. So you can also write this mathematically as so basically this is again the indicative function, okay, that we used I before. So basically you are looking at this is your model HX, okay, on sample X, and then this is the ground truth from the training set, and then you basically count how many of them disagree. Okay, you sum over all the samples in the training set, and then if you like to take the average. Okay, so this is the training error or the training loss that we use on the classification setting with the 0-1 loss. Okay, so this is the training error. So this is what we can measure because if you want to evaluate this training error, so all you need to do is to look at all the samples in the training set. And in the training set, you know the output, okay, because this is provided in the training set. And moreover, you know your prediction on this X, right, because you have the model. And so this is something you can measure. Agree? So training error is easy. But however, well, when we say we want to pick the best model, so later on when we talk about the neural networks, say for example, you have to pick, well, how many hidden units, how many hidden layers, and so on. Okay, then you may not want to pick a model which minimizes the training error, because say in the regression case, this is pretty obvious. So suppose that we want to do regression on this data set, and then you can see that this data set intuitively, it is pretty noisy, right? Okay, so say for example, well, this is a time series data, this is time, and this is your weight, say for example. Okay, and so obviously, well, the measurements here are pretty noisy because obviously your weights will not fluctuate that much over time, right? So if you just pick a model which perfectly fits all the points, then, well, you may want to pick something like this. Okay, but then the point is, well, maybe the underlying trend should not be that complicated, right? And so you see all these fluctuations because your measurements have noise. And so what we want to do is that, well, this is the training data. We are not really interested in fitting all the training points very well. Okay, of course, you have to fit it pretty well, right? So the training set is kind of like what? So if the test set is kind of like the final exam, then the training set is like what? Huh? So maybe it is like before you do the final exam, or maybe, no matter whether you are from Hong Kong. So how many of you are from Hong Kong? So in Hong Kong, well, before going into university, you have to take the DSE exam, okay, or in mainland China, before getting into university, you have to do the Gaokao, okay, and of course, no matter whether you do the DSE or do the Gaokao, you have to do some preparation, right? So how do you do the preparation? Simulation, you have to look at some past papers, right? And then see whether you can do well on those past papers or not. Okay, so the final exam or the Gaokao or the actual DSE, okay, is kind of like the test set performance. Okay, so this is what you really care for. Okay, and then those simulation or those past papers basically are kind of like the training set. So the point is, do you want to do well on those training sets? So you're preparing for Gaokao, okay, you take last year's exam, you get 5 marks out of 100, will you be happy? No, right? So the point is that still, you don't want to be performing too badly on the training data. But even if you get 100 marks, okay, on last year's Gaokao, will you be happy? You are happy, but does that really mean that you will do well on this year's Gaokao? May not be, right? So maybe, well, somehow you somehow you're particular good and last year's question. Okay, so the point is, well, you are not, at the end, in machine learning, we are not really interested in the training error. Okay, we are not, the goal is not just to minimize the training error. Okay, the goal is to get a small testing error. So we want to do well on unseen examples. So that's why we don't want to fit all the training points so well, particularly if the training data may be very noisy. Okay, so going back to this example, so it is possible that, say, for example, this font is mislabeled, right? So it is possible that, so during the data collection process, somebody has mislabeled, say, for example, I look at your face, okay, this is a male face, but then I mislabel this as a female. It's possible, right? Or maybe this font, okay, this is a red font, but then it should not be here. So maybe the actual position should be here. Okay, but then somehow, maybe I use a red. Maybe the actual position should be here. Okay, but then somehow, because I took the wrong measurement, okay, and so I put it there. So again, the data can be noisy, okay, so that's why you may not want to fit it too well. So that means that at the end, what we are more interested in is the testing error. Okay, in other words, if I draw a sample, okay, randomly from the underlying distribution, so will you misclassify? Okay, so in other words, you can also write the error as the probability that if you draw a point x from this underlying distribution, whether your prediction, okay, hx, will differ from the ground truth. Okay, so that is, if I see a new face, okay, and then will you be able to make the correct prediction? So, of course, well, this is something that you cannot measure because this is a probability, okay, and so you can do some estimation by drawing a test set from the underlying distribution, okay, and then you can use this empirical average, okay, as an estimate of the testing error. Okay, in other words, you draw a test set and then you measure the performance of your model on this test set. Okay, but then still this test set needs to be very large. Okay, and moreover, well, it cannot be infinitely large in practice. Okay, and so that's why, so this is just an estimate. And of course, obviously, the test set should be independent from the training set because, so again, it's like at the exam. Okay, suppose you have midterm and final exam, and then there is overlap, then what will happen? Do you want to have overlap between the midterm and final? So say, for example, the midterm exam is exactly the same as the final exam. Will you be happy? So why are you happy? Well, of course, you have the midterm, okay, and then, so this is the training set, okay, so the training set means that you have the X and the Y, you have the question and answer, right? So you have the question and answer, and then you use that for training, okay, so it so happens that you took last year's Gaokao, okay, to practice, and then this year's Gaokao is exactly the same as last year's Gaokao. So what does that mean? You have seen all the questions and the answers, so obviously you can do very well. Okay, but then this is not a true testing of your performance. Okay, so that's why if you want to do performance evaluation, you want to see how good your model is actually doing. Okay, so this year's Gaokao should be different from last year's Gaokao, right? The final exam should be different from the midterm. But of course, well, they cannot be entirely unrelated, right? So the midterm is machine learning, final exam is on physics. Will you be happy? Of course. The physics final exam questions will be entirely different from the midterm questions. Will you be happy? No, because they are not drawn from the same distribution. So that's why, well, the X need to be drawn from the same underlying distribution. Okay, so this is how we do testing. Okay, so they should be different from the training, but should be still from the same distribution. So that means that's well, anyway, so many of you have taken machine learning, so I suppose you know what that means. So you probably have seen this picture. Okay, so of course, so if you go back to this previous example, that means that if you are given, so of course this is a regression setting. So if you are given a set of points, okay, then you can use this stretch line. So this stretch line is a linear model, so it is very simple. Okay, so this is very simple, so it cannot fit the points very well. Okay, but then you can use this kind of model. This is obviously very complex. Okay, but then it may not be very good. So in this picture, so we have the hypothesis complexity here. Okay, and then we have two curves. One is the training error, the other is the testing error. So what it says is that when you are here, when your model is very simple, just like using linear model to fit your underlying points, okay, or this kind of two-class problem. So you use the linear model, so of course the training error is very high. And intuitively the test error will also be high. Okay, so if you increase the complexity, so instead of using a linear boundary, you use a quadratic boundary for this data set. Will it work? It will work better than linear boundary, but still, it will not give you very good performance, right? So that means that when the complexity is here, still you are able to reduce the error a little bit, but still it will not work very well. On the other hand, if you use a very complicated model, so it will be in this region, then of course the training error is very good. Okay, so just like the previous example, you use this to fit all the points in a regression problem. So the training error will be equal to, so you fit this curve, okay, to the points in the regression problem. So the squared error can go to 0. Okay, or you use a very complicated boundary that we saw on the first slide. Then the boundary is so complicated, then the classification error can also go to 0. But intuitively, although the training error can go to 0, but then the testing error will be very high. Okay, because you are kind of fitting the noise. So that's why there is a trade-off here. You cannot be too simple, you cannot be too complicated. So generally, the training error will decrease when the model gets more complicated. But then, if you look at the testing error, it will decrease, but then up to a certain point, it will increase again. Okay, so what that means is that if you want to pick a good model, so recall that you want to have good testing performance, not training performance. Okay, if you want to have perfect training performance, then you have to go here. Okay, but then for good testing performance, you better stay there. Okay, so that's why you should not pick a model which is too simple or too complex. Or later on, when we talk about neural networks, but anyway, all of you know neural networks. Anybody who doesn't know what is a neural network? Good. So if you have a neural network, then a very simple model means that you may have very few hidden units or hidden layers. Okay? Or so this is bad. Okay? And similarly, if you have too many hidden units or too many hidden layers, so again, this can be bad. Okay? So this is overfitting. Okay? So this is what all of you know. And so I guess, how many of you don't know what is cross-validation? A few. Okay, so basically 2, 3. So anyway, so we will go talk about that in that case. So now I want to pick the best hypothesis. Okay, so how to do this? So of course, as I said, I want to go to this point. Okay, but of course nobody will tell you where is this point. Okay, so what should I do? So there are several ways of doing this. One way is that typically, so suppose that you want to build a model for a particular problem, okay, and then somebody will give you the data set. Okay, so again, just like if I want to do gender classification based on images, okay, I have to collect all the face images from you guys, and then you have to label them whether you are male or female, okay, and then I will have a big data set. Okay, and then, so if I were the user, I will give you this data set, and then I will ask you to build me a model, a classifier. Okay, so now you have all the data, so what should you do? So it is kind of like when you prepare for your DSE or prepare for your Gaokao. So as I said, you typically from India. So in India, do you have something similar? Huh? Yeah. So anyway, so you have some university entrance exam. So you prepare for the Gaokao. Okay. So since we have a lot of mainly Chinese here, so you have to prepare for the Gaokao. So what does that really mean by prepare for the Gaokao? So you take some past papers, right? So how many years of past papers? 5 years. Anybody did something different? 5 years of past papers? Okay, you did 5 years of past papers. So suppose that you are preparing for. So Gaokao is in which month? June. June. Also, it is past, right? Okay. So you suppose that you want to prepare for next year's Gaokao. Okay. So that is 2026. So you have 5 years of Gaokao past papers. So that means that you have 2021 to 2025. Okay. You have 5 years of Gaokao. So what will you do? So you just look at all the Gaokao exam, Gaokao questions and answers, and then work on that. That's it. Yes or no? No? So what do you do? What will you do? So I give you 5 years of Gaokao questions and answers, right? So what will you do? You just look at them, okay, and then next year, go. You don't do it this way, right? So what will you do? Yeah, so before next year's Gaokao, you want to have a sense, okay, of how well you may perform in the 26th Gaokao. So how can you tell? Huh? So how to simulate? Suppose that's what, well, of course you can do simulation. Maybe your teachers will do simulation for you. Suppose that you don't have a good teacher, so the teacher is very lazy. Okay, no simulation. Okay, so you got, I'm the teacher, I give you 5 years of Gaokao. That's it, okay. Do it yourself. So what will you do? Yeah, so exactly. So you have 5 years of Gaokao, right? Okay, so you basically want to build a model. Okay, and then you also want to know how well the model will perform. So as a human, what you will do is that you take, say for example, 21 to 24, look at all the questions answered, okay, learn all the basically you are learning the trends, right? Okay, learn the input, output methods, right? Okay, and then you took 4 years of questions, study them, and then you want to see how well you may perform in the 26 exam, and then you try to do the 25 exam. Is it? So that's basically what we want to do in building a machine learning model. Okay, so I give you a lot of training samples, images, image, this face, male, female, this face, female, and so on, so on. Okay, I give you a lot of data like this, and then you want to build a model, and then you want to ensure that the model properly performs well. Okay, so how to do this? So one way is that, well, so this is the whole data set. Okay, so these are your 5 years of Gaokao, right? So what I can do is that, okay, I take all this as my training data, okay, basically to build a model, and then I evaluate this on this part. Make sense? Okay, but maybe I cannot do this, maybe I want to do this. I take this one. So what does that mean? So you said that you use the 25 exam, okay, but maybe I just look at the 21 questions, and then I do 22, 23, 24, 25, okay, and then use that to evaluate my performance. So what are the pros and cons? So if I use this approach, okay, so you have 4 years here, right? 21. Anyway, so this one. So 21 up to 24, okay, and then this part is 25. So if I use this division scheme, so what are the advantages and disadvantages? So compare with this one. I just take the 21 and then use 22 to 25. So how many of you will pick the left approach? The right one? So how many of you don't know what to do? So you have done the Gaokao. Okay, so I suppose many of you or all of you have done something like that. So what's the problem with the left approach? So basically, okay, you learn very well. Okay, you look at 4 years of Gaokao. Okay, so you know question answer, the mapping. Okay, and then you perform the evaluation on the 25 exam. Suppose that you did very well in this particular year. Does that really mean that you may do very well in the 26th exam? No. Maybe because, say, the 25 Gaokao is particularly easy. Okay, then you may have a false impression of of your performance. Okay, so in order to have a better performance evaluation, so what can you do? So instead of doing only the 25 Gaokao, so you can go to the other extreme, which is on the right hand side. Okay, you take 22 to 25, 4 years of Gaokao, okay, as your performance evaluation, right? So if in all these 4 years you get 90, then that means that, well, it's likely that you may get something similar, okay, in the 26th exam. Agree? But then what's the problem? The problem is that you only look at the 21, okay, exam. So that means that your training set is very small, and so you may not learn very well. So there are pros and cons. Okay, you use a large amount of training data, you have a good model, but then the performance evaluation may not be reliable. Okay, you use the right-hand side, then you use very few training data, the model may not be good, but then you have a good performance evaluation result. Okay, so that's why, well, of course, intuitively, many of you will do something in between, right? So say, for example, you may want to use 3 years of Gaokao exams to do your training, okay, and then use the remaining for evaluation, okay? So this is again typically what you can do, okay, for machine learning. So again, what that means is that you are given the whole training set, the whole data set. You don't use everything for training because you want to do performance evaluation, okay? So you use parts of that for actual training, and then the remaining part is for evaluation, okay? We call this the validation set. Okay, basically it is just to give you an estimate of your performance. So this is not the real test data set, because in a typical scenario, okay, the user gives you this data set, but then at the end, well, he or she, the company, will have its own data set for evaluating your model. Okay, or just like in the Gaokao, so I will not use the 21 exam result, okay, your performance of the 25 exam as the Gaokao result. Okay, I will ask you to do the 26 exam instead. Okay? So, but of course, how to draw this line? This is subjective. Okay, so if the data set is very big, then this may not be very important. Okay, but then if the data set is small, then you should avoid using here or there partitioning. Okay? And then of course, well, so suppose that you have well, maybe even in the human case, human learning case is the same, right? So suppose that you have used 3 years of Gaokao exam, okay, for training, and then 2 years of Gaokao exam for evaluation, and now you have an idea of how good you may perform in the 26th exam. So you got, say, 80 marks. So is that the end of the story? So you are happy and then go to the 26th exam? So you look at 3 years of Gaokao, use 2 years for evaluation, and then, okay, you got 80, seems okay. 80, are you happy with this? I don't know the Gaokao score. Gaokao score is usually 6. What's the total? The full mark? 700. 750. Okay, so what is a reasonably good score? 600. Okay, so say for example, you do this procedure, you get 600. Okay, and then maximum is 750. So will you be happy? 600? suppose you want to go to Beida Tsinghua, okay, and then you get 600, okay, so what will you do? And then you are happy enough, and then you just do the 26 exam? Huh? So suppose you don't have more data. Oh yeah, that's a good point. Okay, in machine learning, again, we want to do the same thing, right? So obviously you want to go to Beida Tsinghua, maybe you don't want to do only 5 years of past papers, right? You want to do 10 years, okay, 20 years, okay, wherever. But again, suppose that you only have 5 years of data. That's all. Recall that typically in a scenario, maybe this is all the user gave you. Okay, you have 5 years. So what do? You look at 3 years of data in detail, you do performance evaluation on 2 years of data, you got 600. So what can you do next?
Randomly pick the other 3 and just evaluation on the other 2. Randomly pick.
Yeah, maybe okay, but then what we suggest here is that, okay, so you have done this, and then you got 600 marks, okay, and then so the last 2 years are just for evaluation, right? But then you again, so now you want to basically improve, okay? You want to get better, okay? Instead of 60, you want to get 650 maybe, okay? So how to do this? Okay, so you now take in more training data, okay? How to take in more training data? You can retrain the model, okay, by using the remaining 2 years. So for the performance evaluation, of course, so this may be different from machine learning, may be different from human learning. Okay, for machine learning, okay, model selection, again, say for example, we are using neural networks. Okay, maybe I have several choices. Okay, I can use, say, one layer, hidden layer, layer neural network. Suppose that for simplicity, I can either choose 1 layer or 10 layers. Okay, and then after using this procedure, I found out that using 10 layers is better than using 1 layer. Okay, but then I want to still improve on this 10-layer network, and so what I can do is that I use the remaining 2 years of data to further train the network. Okay, but of course, this is not possible may not be possible for humans, right? You cannot take several models. Okay, but anyway, so this is the analogy. So the point is, after the evaluation, maybe you can use the remaining data to do the training again. So the point is, as shown in this trade-off, so the larger the training set, the better is the model, okay? But the larger the validation set, the more accurate is the performance evaluation. Okay, so that's why you want to have a trade-off. So it really depends. So say, for example, you can use 1/3 for evaluation, the remaining 2/3 for training, okay, and so on. But then, going back to this Gaokao example, okay, so you have 2021 to 25, you use 24-25 for performance evaluation. But then it's also possible that 24-25 are easier, right? So that means that if I use 21-22 for evaluation, I look at 23-25, then maybe you can get a different performance evaluation. Agree? So again, you can have many different ways of deciding which one is for training, which one is for validation. Okay? So again, as a human, well, you have done this wrong once. Okay, you have used 21-25, 23 for training, and then 24-25 for testing. Then that's it. But then for machine learning, okay, so you can in fact do this partitioning multiple times. Right? For human, you cannot do this because you remember something. But then for machines, okay, you can repeat this process. So you have 2 models, one neural network with 1 hidden layer, the other neural network with 10 hidden layer. Okay, you can use one partitioning, obtain performance results, and then use another partitioning, and then obtain another performance results. Okay, you can repeat this process multiple times, and then take the average. Okay, so that will be more reliable. Agree? But then, of course, well, that means that you have to repeat the process with different partitioning. But then this is a bit not so disciplined. Okay, so I can cut it here, I can cut it there, I can reshuffle, and then cut it there, and so on. Okay, so we want to have a more disciplined way of doing this evaluation. So basically, I want to repeat multiple times. but I want to be more disciplined. So that's why we have this cross validation. Okay, so I suppose seems that 80% of the students know what is cross validation, right? So first of all, you have to specify how many folds. So this is an example. So this is the data set that you are given. Suppose that you are given 1,000 samples. Okay, so the user gave you 1,000 samples. And then again, as I said, you have to cut it into training and validation. So in the previous approach, I just cut it somewhere. Okay, but I want to do multiple repetitions. So how to do it in a more disciplined manner? So here we use so-called 5-fold cross-validation. So what that means is that I cut these 1,000 samples into 5 parts. Okay, so of course, if you have 1,000, then each pass will have exactly 200 samples. Okay, of course, in practice, you may only have say 999 or 9910, wherever. Okay, then you just try to cut them into almost equal parts. Okay, it doesn't really matter that much. So suppose for simplicity, we have 1,000 samples. I cut it into 5 parts. Each part has 200 samples. Okay, so what can I do? So I do 5-fold cross-validation. So what that means is that, so I have, let me see if I have a better picture. So let's call these parts A, B, C, D, E. Okay, so I have 5 parts, and then for 5-fold cross-validation, so just like before, I have to do training and I have to do validation. Okay, so if you have 5 parts, then, so for those who know cross-validation, so what can I do? So first, you can train on, I can train on A, B, C, D. Okay, and then I train a model, and then I evaluate on the remaining part. So this is basically cutting this, using this for training, using that for validation. But again, as I said, where to cut? I can cut here, I can cut there. So that means that at the next round, I can try to train on, say, A, C, A, C, D, E, okay, but how come? Maybe we use some more disciplined way of doing this. So suppose I train on A, B, C, E, right? If that's the case, then I evaluate on D. And then next I can train on A, B, D, E, and C, and then A, C, D, E, and B, and then B, C, D, E, and A. Right? And so of course, when you are doing this, you train on this, you will get an error. Okay, error 1. Okay, in the second round, you have another error measure because you are training a different model, you are doing evaluation on a different data subset, and so on and so on. So at the end, you will have 5 numbers. Right? So in other words, you have repeated this process 5 times, okay, based on different partitioning of the data. And so you have 5 numbers, so you think the performance, you can obtain the performance by, so you have 5 numbers, so you just take the average, right? Take 105 and then summation. Okay, so that will be your estimated performance of the model. Okay? So this is called the 5-fold cross-validation. So as I said, so basically in general, when you want to do K-fold cross-validation, and then you just cut it into K parts, and they have to be disjoint, because again, just like before, you will use this part for training, and then you use this part, remaining parts for evaluation. Okay, and so you don't want to have any overlap between the validation set and the training set, because otherwise you are basically you train on the 2025 Gaokao, and then you perform evaluation on the 2025 Gaokao, then of course you can get 750, right? Okay, but then that doesn't mean that you will get 750 next year. Okay, so there should be no overlap. Agree? And so you repeat this process K times. So here 5-fold, you do it 5 times. Okay, and then you use one of the set okay, subsets for validation and the remaining for training, and then at the end you average the performance. Is it clear? So this is the cross-validation procedure. So why is this good? So this is good in the sense that it is more disciplined. In particular, you can see that if you have, so you have a lot of samples, right? This is the data set that you are originally given. So you can see that each sample is used how many times in the validation set. So suppose that I do threefold cross-validation, okay, for this particular sample. This particular sample, okay, so that will be used for validation how many times? 3 times. So recall that's what you do. Say threefold, you cut it 3 parts. Okay, and so this sample will be used for validation when you train on these 2 and evaluate on this. Okay, so each sample will be used in the validation set once, okay? And how often will they be used in the training set? How many times? So again, for the threefold example, so this sample will be used how often times? So you have to do the training and evaluation 3 times, okay? So this sample will be used for evaluation once, and then will be used for training twice, okay? So in general, it will be k-1. So that means that each sample will be used in the validation set once and used in the training set k-1. So this is more disciplined compared with this random partitioning thing because, okay, I cut it here, then maybe some data sets will be used for training many times. But then, but here, if you do cross-validation, so all the samples are treated the same, okay? And moreover, during training, so you use quite a large portion of the data set because for k-fold cross-validation, that means that you use k-1 over 1 over k, okay, of the samples for training. And then you use 1 over k for testing. Okay, so this is better than, more disciplined than k-fold cross-validation. So, but then of course you have to set the level k. Okay, so in practice, again, that depends on the data set size. So the problem with a large K is what? You can use a large K, right? So what's the problem with a large K? So validation is very small. So suppose that's okay. Now I have 1 million samples, okay, and then I do. Yeah, exactly. Say you have 1 million samples, okay, and then you do 100-fold cross-validation. Okay, so in general, you do k-fold cross-validation, you have to repeat the process k times. Okay, so just like here, you do 5-fold, you have to do 5 training. Okay, so depending on what model and how long is the training time. So if your model is quite complicated, say deep network, okay, and then training time can be pretty slow. Okay, it may take you say 1 week, 1 month to do 1 training. Okay, and then in that case, do you still want to do 10-fold cross-validation? No. Okay, so if I ask you to do, if you want to do 10-fold cross-validation for your project, okay, each training takes 1 month, then that means that you will not be able to submit your report. Okay, so obviously that depends. Okay, so if you have lots of data, big models, then typically you don't need to do cross-validation. So that's why in deep learning, so most of the papers these days don't do cross-validation. But of course, if you use small models, so in this course we will also talk about some traditional models. So say for example the decision trees, okay, then it is pretty fast, and then you can do k-fold cross-validation with a much larger k. Okay, and so suppose that the training time is not important. So in principle, what is the possible range of k. So you are given a data set, okay? So the smallest k can be what? K. Can you do one fold cross-validation? No. How to do one fold cross-validation, right? So basically you have the same thing. So the smallest is at least you have to do two-fold, okay, right? And then what is the largest number of k? The number of samples, right? So if you have m samples, okay, then the largest number of value of k will be equal to m. So in that case, what are you doing? So that means that if you have, say, 100 samples, okay, you do 100-fold cross-validation. That means that in each run, you take how many samples for training? 99, and then evaluate on 1. And then you repeat the process 100 times. Okay? In each run, you basically leave out one sample for validation. Okay, so that's why this procedure is also commonly called leave one out cross-validation. Okay, or sometimes it is just written as LUCV. Okay, leave one out cross-validation. Okay, but again, as I said, so typically this is possible only when you have a small data set. Okay, and the model is pretty easy to train. Otherwise, it will be very expensive. So diagrammatically, this is what you have. Okay, you just leave out one single sample in each run. Okay, you train on the rest, and then evaluate on this one, and then repeat. Oops. Okay. So let's see. So we can either stop here. So you guys are okay. Maybe we stop here then. Okay. Okay. So see you next week. So any questions? No? Okay. So next week we are going to talk about nonlinear models. Bye bye. Yeah.